Hello and welcome to my presentation. My name is Benjamin Finley and I'm a postdoc at the University of Helsinki. And my topic today is context-driven encrypted multimedia traffic classification on mobile devices. So first I'll talk briefly about the motivation for the work. A major motivation just in multimedia traffic classification in general is the huge growth in multimedia traffic. And this has only become a bigger issue given the pandemic, which has seen huge growth in, for example, web conferencing traffic and video on demand traffic. Beyond this, we've seen the introduction of user-centric networking applications, such as private virtual networks and Middlebox Zero. And these applications actually allow end-user device control of certain network policies, such as quality of service handling. However, a major issue with these applications is that they lack a privacy-preserving traffic classification approach to differentiate different types of multimedia traffic. So most existing multimedia traffic classification approaches are network-centric, and they rely on things like root certificates or certificate pinning to enable deep packet inspection on encrypted packets, or they leverage, for example, deep learning approaches that learn various application-specific signatures, for example, from initial SSL or TLS packets. So the issue with both of these existing approaches is, as I mentioned, the privacy issues. Even with the deep learning approach, sometimes in certain contexts, even the application itself can be sensitive. So in addition to this, certain applications can produce multiple different types of multimedia traffic. You can imagine a Skype where you can have just an audio conversation or an audio and video conversation. And then we might want to differentiate between these two contexts within a single application. So given this motivation, in this work we present Mediasense, which is a privacy-preserving approach that classifies multimedia traffic from any arbitrary multimedia application into a specific multimedia activity category, which we call a multimedia context. And I'll go more into depth in that later in the presentation. And we do this by using a set of general non-app specific features that are based on the I/O component statuses of the mobile device itself. So first, as I mentioned, Mediasense classifies traffic into what we call multimedia contexts. So here we illustrate these multimedia contexts through a hierarchy sort of tree diagram. And the actual contexts are then represented as these 11 nodes at the very bottom of the tree. So the first layer of the trees here denote the fundamental type of interaction. These can be this multimedia production, multimedia consumption, and conversational multimedia. Whereas the second layer denotes the actual type of content produced, consumed, or exchanged during this interaction. So this is either audio or audio plus video. And finally, the third layer represents the context according to the source and destination, along with transmission of this content. So specifically, local implies that media production or consumption without any IP communication. So for example, audio record here means you're recording an audio clip, for example, on your smartphone and saving it locally to the device. And we note here also that, for example, in conversational multimedia, when you have audio without any IP, it's actually represented as a sort of GSM or voice over LTE conversation. We argue that these multimedia context categories are relatively broad, yet they're still useful for many purposes, including the sort of network optimization or quality of service applications that we envision. So here we illustrate the relationship between the device I/O component statuses and the multimedia production contexts. So as I mentioned, we basically leverage the statuses of different components on the mobile device. And here we show that we actually leverage 5 different components: the camera, microphone, speaker, display, and then a network interface. So we start out here with the initial state before any multimedia context. And for example, for video recording here, we show that the camera, microphone, and display are on, binary 1. But the network is not on, as the video is being saved locally, for example. And we also show here the transition, or for example, for these audio contexts, where when you initially start the audio production context, the display is on from interacting with the application, but then it can turn off eventually over time and lead to these other types of component statuses. So, and then we show on the right-hand side here the I/O statuses for a Periscope live video broadcast. It's just an example for an example app in this production context. So we can similarly illustrate, have a similar diagram that illustrates this for the consumption context here. And then also for an example consumption app here, we have this tune-in audio streaming application, and we have the different component statuses for that application. And finally, we have here for the conversational context, a similar diagram. And we also note here the bidirectional arrows, of course, because that the context can change within a single application. If you imagine, for example, in Skype, someone turning their video signal on from previously having a voice-only conversation. And then on the right-hand side, we show the I/O states as an example for a WhatsApp audio call. So one of the potential issues with using I/O components for this type of classification is so-called mixed contexts, where you might have multiple multimedia applications that could utilize some I/O components simultaneously. So we actually performed experiments to determine the limitations of this on Android and iOS. And we found that luckily most of the contexts are not possible. They're not possible to have both contexts simultaneously. So the only combinations that actually worked were streaming audio during a VoIP call or consuming or playing 2 separate media at the same time. Thus, we think that these sort of mixed contexts should be relatively uncommon and not a major problem for this type of classification. Another significant challenge with this type of system is actually the classification between IP versus local contexts. So to solve this, we use actually network traffic features. And here it shows in this table some of the rule-based logic that we use for this classification, which is primarily the bit rates in either the uplink or downlink direction, as well as this fast start bytes, which is basically data volumes downloaded during the first 10 seconds of streaming. And this special variable is needed because of the initial buffering of streaming audio and video situations. And basically, we later check the performance of this classification logic to show that it's adequate and it works well for these contexts. And relatedly, we also have to be able to identify the specific network flows that are associated with the specific multimedia applications that are driving the contexts. So this is important and related to the previous slide in the sense that we only want those rules to apply to these multimedia flows. And it's also important in terms of being able to pass this information to, for example, that user-centric networking app or network provider. So only those specific flows can be handled according to that context. So, and basically we define the network flows as these sort of 5 tuples. And to identify them, we use a sort of filtering approach with different tempo thresholds for different context types. So we look for network flows that start, around a time window around the same time of when the actual multimedia context begins. So, for example, for this conversational context, we use a 3-second window around the media start. And we also later, I'll show you later, we also check the performance of this identification task. So in terms of actually implementing the Mediasense system, we implement it as a user-level Android service with 1 Hertz level sampling or checking of these multimedia components, and then lately the multimedia contexts. And luckily, most of these components don't require explicit user permission to check, except for the Media Recorder API, which is actually related to the microphone. So for this, we do request explicit user permission. We also require use of the Android VPN API, and this is so that we can monitor those aforementioned 5-tuple network flows and also calculate basic network flow statistics. So, however, we don't use any root certificates or deep packet inspection or anything like that. It's all strictly for that network flow feature extraction and monitoring. We also check for the battery impact of the Mediasense service. So basically, we check the current consumption on an Android device over a 60-second period with different multimedia applications, and we find that the overall service has a quite minimal impact on battery life due to its quite lightweight nature. So we find that it consumes about 70 milliamps per hour average while the device is idle, for example. And you can see here in the table the other sort of comparisons for different applications and the consumption increase there. For the evaluation of the Mediasense system, we load Mediasense on an LG G5 with Android 8 connected to an LTE network. And we then collect a convenience sample with 52 popular multimedia applications. And then we generate usage sessions from these applications by exploring the main multimedia context of each application for 30 to 60 seconds. Then using these captured sessions, we then evaluate for Mediasense both the session classification, and this, as I mentioned before, relates to, specifically for this, whether it's an IP or local context, and also the flow identification performance, so how well Mediasense can actually identify the flows that correspond to a specific multimedia application. And finally, we also evaluate the generalization performance to novel multimedia applications. Of course, for Mediasense, since we don't use actually any application-specific features, the generalization performance is essentially the same as the flow classification, or flow identification performance that we'll discuss in a second. So in terms of local versus IP classification performance, we see here that in each of these context areas, the Mediasense performs very well. Actually, with some minor misclassifications in the video consumption or video streaming area, and this is due to some low bit rates. So those video streamings was actually misclassified there. But otherwise, the performance is quite strong. Whereas in terms of network flow identification, we also find that Mediasense performs quite strongly with only a few misclassifications and misidentifications in the audio and video stream contexts. And these are primarily due to some background flows that impacted the classification. For comparison, we leverage two different deep learning approaches to multimedia traffic classification, specifically this deep traffic, which is a session or flow level classifier, and then deep packet, which is a packet level classifier. And for these evaluations, we similarly split the flows sessions or packets, depending on the approach, 80% training and 20% testing. While for the generalization testing, we split the flows and packets similarly, but the test split contains only those flows or packets from apps not in the training split. So as a quick background, deep traffic at the session level uses the first 784 bytes of each session or flow, and it converts this to an image, and then uses 1D or 2D convolutional neural network for the actual classification into different multimedia traffic classes. Similarly, deep packet uses the actually entire packet, the 1500 bytes of each packet, with the IP address masked out, and similarly uses 1D or 2D convolutional neural networks. A little bit different also in this for this deep packet approach is that we need to do sort of random undersampling or some type of imbalance learning approach. Because different classes, of course, have similarly different packet volumes. For example, audio versus video classes. So first, if we look at the performance of deep traffic, which in this case we have this session level performance. We said it performs fairly well for many of the categories, but there is still some performance issues. And these are potentially due to apps that, for example, have both the video and audio components. And then, like Skype, where it might have both the video, audio only and audio plus video options. So these might have similar starts to the session or flow. And then, of course, deep traffic won't consider or only considers the start of the session or flow. So then you have potentials for misclassification. Whereas if we look at deep packet, we find that the performance is significantly better. And in most cases, except for this audio streaming versus audio streaming classification. We leave this to future work to identify exactly the issue with that. But basically, deep packet performance is partly due to the very specific application features that it learns from each packet. But the performance overall is very good. Finally, we illustrate the generalization performance of Mediasense versus the deep learning approaches. And we can see here that the Mediasense has much better generalization performance. And this is primarily because it does not leverage application-specific features like the deep learning approaches does. So this allows it to generalize better to new applications. This also helps with preserving privacy, as the potentially sensitive app-specific features do not need to be contained or held by the networking applications or the network provider, as in the deep learning approaches. Thus, for example, the traffic could even potentially be obfuscated to help protect against app identification by the network. But even with this obfuscation, it would still allow, for example, for Mediasense to work and for it to apply these, for example, the QoS mechanisms that I was discussing before as a potential application. So beyond the existing implementation of Mediasense on mobile device, there's also the potential that Mediasense could be extended to other device types, for example, like desktop or laptop computers or other types of handheld devices. Additionally, beyond that, we see that there might be additional uses for the network context information that Mediasense generates. For example, it could be used in network selection in multi-homing. You can imagine that a device that has, for example, multiple different network connections, Wi-Fi, LTE, 5G, or something like this. And the idea is that you could dynamically select which network to use, partly based on this contextual information. Additionally, you could do even device-specific applications, such as plugging or unplugging certain cores or scaling the CPU frequency by the CPU governor. You could also schedule background tasks according to the type of multimedia application being used. Or even things like, for example, in 5G, where you basically mark different flows with the so-called DSCP, which is differentiated service code points. Operators can mark these flows depending on the information provided by this type of Mediasense service, and then this could allow different slices to be used for different flows or different type of multimedia contexts. So in conclusion, in this work we presented Mediasense, which is an approach for privacy-preserving device-based multimedia traffic classification. And to this, we leverage the statuses of device I/O components. We show that it provides a strong performance comparable to, for example, existing deep learning approaches, but also provides much better generalization to new multimedia applications compared to those other approaches. We also argue and show that the type of contextual information that it provides is useful for a variety of applications. For example, as mentioned with these user-centric networking applications, or even in more exotic areas like, for example, network selection and multi-homing, or CPU scaling. So thank you for your attention, and I'll take any questions.